Swayam Prabha. Digital India. Educated India.
All right, hello everybody. So welcome to this session on construction materials and methods. I am Manu Santhanam. I am working in the Building Technology and Construction Management Division of the Department of Civil Engineering at IIT Madras. And I specialize in construction materials, primarily concrete, and my research is based on concrete technology. So today I'll give you a glimpse of what is out there in terms of construction materials and practices. Oftentimes what we see is the evolution of materials deals with the way that we try to construct with these materials. So the kind of construction practices are driven by the kind of materials that we actually have. Okay? So I'll take you through a journey through the use of different types of materials and where we are currently and where we are going from here. Okay? All right. So I'll start with talking about why we want to study construction materials. What governs material choice? How do we actually decide what material is best for a particular situation? We'll look at some historical evolution of materials and methods. I'll specifically talk about masonry and concrete because that's the most relevant in terms of materials for the Indian context. That's where we use mostly masonry and concrete type buildings. We'll look at some examples of iconic structures with different materials and look at some interesting aspects about the construction methodologies adopted in some of these structures. And finally, we'll end with a look at the challenges in material science and practice. So of course, you know very well that there are several different types of civil engineering materials that are available today. Common ones being steel, concrete and asphalt, wood, polymers and plastics. You have other metals like aluminum, copper, which are also used in construction. Of course, today we are talking a lot about using composite materials, which was earlier used in aeronautical, mechanical engineering. Today we start using composite materials also in civil engineering. So of course, you know very well from what you've seen around you, you've observed quite a bit that concrete apparently looks to be the material that is most widely used, right? In fact, it's the second most consumed material in the world. After? What is the first most consumed material? Soil, so if you consider soil as a construction material, yes, we use a lot of soil in construction. Somebody said the right answer before. Water, yeah, water. Concrete is a material that is consumed in quantities which is second only to water. So significantly large content of water is actually consumed for several things, of course, including construction. But concrete is the second most consumed material. Apparently, we are using about 25 billion tons of concrete every year. 25 billion tons as per the last estimate. And it's only bound to go up because we know that in countries like India, in several African countries, in several other Asian countries, there's a lot more work that needs to be done regarding development of infrastructure, and that's where concrete is going to be used more and more. So obviously, there's a heavy burden that we are placing on the environment, and these are some of the aspects that we'll look at towards the end when we look at the challenges as far as material study is concerned. All right. For now, let's look at why do we want to study materials? I mean, they are available, let's just use them, right? But there are several different aspects why we want to actually engage in a deeper understanding of material characteristics in order to make our construction more appropriate and more sustainable, more durable in the long term. So idea is to improve the quality of the existing materials and enhance the performance and service life. So later, when you learn other aspects of engineering, you learn about service life being one of the controlling factors which governs the choice of a given material or a construction product or a process, right? Service life essentially deals with how long is the material or the structure able to withstand its given environment without losing its quality with which it is actually performing. The other aspect is we want to always look for new materials, primarily looking at cost effectiveness and materials that are actually durable and long lasting. So that's another aspect why we want to understand materials deeper from a scientific point of view. Utilization of waste today is turning out to be quite a big challenge because we have to extensively dispose a lot of waste that is generated from different types of industries. In many cases, we find that construction is a scenario where we can actually utilize many of these waste products, but not because we are just putting waste in the material and expecting it to perform, but because a lot of the waste can actually end up being a value added resource to construction materials and projects. So waste utilization is another aspect why we want to study materials and understand the effect of these materials on the existing construction materials. And of course, we have infrastructure which is ailing, getting old. We need to understand how materials degrade with respect to time so that we can decide on appropriate strategies for repair and rehabilitation with which we can prolong the service of these existing structures. You know, you all traveled by trains and you've seen many of our railway bridges are on the verge of actually deteriorating to a state where they can't be probably recovered anymore. So because of that, we need to understand how the material behaves with time and try to service the ailing infrastructure so that we can extend the service life of these kinds of structures. All right. So there are several factors that govern or influence the choice of materials, right? First and foremost, of course, depending upon the type of application, what exactly are you constructing? What material is locally available and available at a cost effective sort of so cost should be low and the material should be available aplenty locally. And that's probably the most important factors with respect to the choice of material. Of course, in certain areas, the climate will govern the choice of a material. For example, if you go to the northern European countries where very little daylight is available most of the time, you could use glass as one of the major materials of construction because it allows in a lot more light. But unfortunately, in India also, we started copying the Western use of glass, and most of our IT buildings and structures have also come up with these glass facades that are completely enveloping the building. What is the problem with using glass in a climate like ours? It brings in a lot more heat into the structure. And because it does that, we spend a lot more energy trying to air condition the buildings. So we are sort of losing the battle when we try to choose materials and technologies that are not really apt for an environment. So the climate is one of the deciding factors why we want to choose a particular material for a certain location. The other aspect obviously is the performance requirements. What exactly do we want this material to do, right? What kind of engineering characteristics are expected from this type of a material? So that's the performance requirement. Aesthetics, again, is an important factor. You obviously want to choose or build structures that look good. And in many circumstances, the same material may not look or give the ideal aesthetic qualities in different types of structures. And finally, of course, one thing which we have neglected so far, but we are beginning to realize that it's important, are the environmental concerns about the use of these materials, like energy content, the raw material usage, depletion of natural resources and things like that, and emissions that we have related to the production of the material itself. Okay, we'll talk briefly about that towards the end of this lecture. So let's look at how materials and methods have evolved over the years. Okay, this sort of is a historical process, but it's not probably entirely accurate in the way that I've depicted the different materials and processes, but idea was to give you a comprehensive glimpse of what type of construction materials and processes are actually undertaken by engineers to build the types of structures. So we have monolithic construction, probably the oldest variety, where people simply built out of carving rock, right? So the caves are the earliest example of a dwelling as far as human civilization is concerned, and these caves were actually built into the existing mountains by simply drilling and knocking things down and making a space for yourself inside. So just to create a safe space for yourself, right? Later on, people realized that they had to work with smaller blocks of material so that they could actually construct in a lot more grander fashion, because you can only do so much as far as monolithic construction is concerned. You can't really go beyond a certain scale. So then they started looking at smaller blocks, assembling these blocks in various types of shapes and sizes, and that's what we call as masonry. Of course, along the same time, wood was also quite highly prevalent in areas where wood was available. Good quality wood for construction was available, and wood as a construction material probably dates back to as long as masonry has been used. Later on, we entered the era of concrete, and people started realizing that you can actually optimize further the combinations of different types of materials to give you certain very interesting characteristics, right? For example, in the fresh state, concrete is flowable, which makes it possible to cast it in different types of shapes, which is not possible with masonry all the time, which is not possible with monolithic construction also. From concrete, we entered the era of reinforced concrete and steel. With more and more steel being utilized in our buildings, we started realizing that we can actually do things to buildings which we could not envisage with either masonry or concrete, primarily because we are utilizing the property of steel of its high strength and ductility. And with that, we could actually start optimizing the usage of materials and build structures that were a lot more cost effective, could take a lot more load, and could perform exceedingly well in disasters such as earthquakes. And then moving on from there, we are encountering today several examples of composite construction, and in the long term, we are looking forward to the use of smart materials and sensing materials that can actually govern the performance of the structure as we live in it and adapt the environment to suit the needs of the inhabitant. So these are smart materials and structures, probably the way to go forward in the future, but a bulk of our building construction stock will still be in concrete and steel, and that's what we are primarily using today as a construction material in India. All right, so some examples here of monolithic construction. This is all too familiar for you. The figure on the right, can anybody tell me where that's from? Sorry? It's from, oh, of course it says there, it's from Hampi. Okay, it says on the slide, it's from Hampi. It's basically a chariot which is carved out of a single rock, right? On the left, you see another picture from Ellora. Yeah, you see that again from a single rock, you've carved out an entire temple, right? As you move forward towards masonry, the simplest examples of masonry are the dry stacked masonry. So you just take blocks and keep it on top of one another. And how is it stable? Because of gravity, because of sheer mass, right? You use really massive components, and as you go to the top of the structure, you keep on reducing the size of these components. Like the Great Pyramids of Egypt are essentially dry stacked limestone blocks that were kept on top of each other and ultimately resulted in a massive structure, which even today is a fairly significant landmark in the world. Moving on from dry stack masonry, then people started realizing, okay, to really achieve such feats, you have to be superhumans, right? Lifting these blocks. I don't know if anybody reads Asterix in this room. You must have read Asterix in Cleopatra, where they drink this magic potion and lift all these blocks and build all these wonderful structures. So something like that must have happened to really make these workers lift all these blocks, or they would have had very good engineering techniques to lift these heavy blocks to get them placed one on top of each other, right? But moving on, people thought this was not really the best way to move forward. Let's look at some ways to join these blocks so that we can work with smaller blocks that people can carry quite easily, right? And that's where the jointed masonry started being practiced. And jointed masonry even today is practiced. Only thing that is changing in jointed masonry is the type of cementing material used to bind these blocks together. So in the past, you have several other examples. I'll come to that binding material part a little bit later. Today, of course, we only think about cement as the only possibility as far as joining masonry blocks are concerned. So these are some examples. On the left, you have a brick masonry structure, and on the right, you have a stone masonry structure. Both of these have very fine detailing work done with the joints, and that gives a very nice appearance to the entire structure. Moving on from jointed masonry, you can actually get a lot more optimization with the speed of construction. Please remember, when you are doing a jointing process in a masonry block, you are placing one layer of masonry, then you have to actually place the cement mortar or lime mortar on top, which is the binding material, then put the next layer on. But you can't keep doing this entire process in a single day. You need to wait for the material to harden. Otherwise, the wall will become unstable and fall, right? So because of that, the use of mortar for joining the blocks is a process that actually slows down the construction work significantly, okay? If you really think about it, it slows down the construction work significantly. So the way around it is to ensure that you don't have to actually put any more mortar, but you can still get good stability by providing interlocking between your blocks. And this is something you all know from your childhood days. You have played with Lego, other sorts of building blocks which you actually connect because of the interlocking capabilities of these sort of blocks, right? And such blocks, basically the interlocking blocks, lead you to have a construction which can be done much faster than what you would have in the case of a jointed masonry. From interlocking, people started getting the idea that you can strengthen masonry structures even better when you have reinforcement put inside the structure. So reinforcement ensures, okay, so the need for providing additional strength to masonry comes in when we actually look at the performance of masonry in disaster events like earthquakes. So in earthquakes, you can imagine that the structure actually has a motion that is moving along with the ground, right? In such cases, just having a good strength in the axial direction is not going to help. So you need to start providing some degree of load carrying ability which can actually take the loads in the lateral direction. In such cases, providing a reinforcement can go a long way in actually extending the load carrying ability of your masonry. So, reinforcements in masonry became the next step in the development of masonry structures, and where you could look at providing certain cavities within the masonry, putting a reinforcement rod like an steel rod that we typically use with concrete, and providing the reinforcement that provides a lateral resistance. So, reinforced masonry was the next step forward from your jointed masonry and interlocking masonry to provide additional load carrying abilities to your structure. But coming back to the jointed part, as I was saying, the primary reason why people went for this was because they discovered or they invented combinations of materials which could give very good binding characteristics, which could join these pieces of masonry blocks together, right? And this binding characteristic is made possible because of the use of different cementing materials. If you will go to the past structures in Egypt and in Greece, a lot of the burnt bricks and alabaster were cemented using bitumen. Now, today we know that bitumen is used to actually pave roads, right? But the same material was earlier found in natural pools. Okay, you know the process of formation of bitumen, right? It's formed from the process of distillation of your petroleum or crude oil. You get several products like gasoline, kerosene, all those kinds of things, and what remains as a residue is asphalt, right? This asphalt also occurs in naturally occurring pools around the world, and people were actually able to extract this asphalt and use this as a binder to bind these masonry blocks together, okay? So, that became the first sort of binding material to start binding these masonry blocks. But later in Egypt, people started using burnt gypsum based cementing material. Something that you would have done in school is to use plaster of Paris as a molding material, right? When you mix plaster of Paris with water, what happens? It hardens because it converts to gypsum, right? Its plaster of Paris is calcium sulfate half H2O. When you add water to it, it becomes calcium sulfate 2H2O. So, it causes hardening of this material, and that again was a very popular binding material used in the past. The only problem with gypsum is it is not highly resistant to moisture. When rain falls on gypsum, it will slowly erode away the gypsum and dissolve it away, because of which the binding properties may get reduced with respect to time. Later on, of course, people started realizing that the best quality binding could be obtained by using lime. Lime is basically your calcium oxide. And where is it obtained from? Where is lime obtained from? From burning of limestone, that is calcium carbonate. When you burn calcium carbonate at temperatures more than 800 degrees, you lose the carbon dioxide. What remains behind is your lime. When you react lime with water, what does it do? It produces calcium hydroxide, right? And this calcium hydroxide again absorbs the CO2 from the atmosphere and converts to calcium carbonate. So, that's the lime cycle. We started off with calcium carbonate, we end up with calcium carbonate. So, that's basically again one of the technologies that people started looking at with a lot of interest, because this had the potential now to actually do massive levels of construction because of the excellent binding properties you got with this lime. So, again Roman structures obviously have several of these structures are still standing, and people have actually looked at the performance characteristics of this lime mortar, and they find that it's actually of a very high quality. In India also, there are several evidences from the past where lime was actually mixed with other additives like ground brick, for instance. The brick itself, when you grind it into a red powder, it enhances the properties when you actually mix it to make the lime mortar. And that was one of the first uses of additive materials into the lime. Later on in Greece and in Italy, they started using volcanic ash, and they saw that when you mix it with the lime, it gave much higher strength and durability properties, okay? So, that's where the word pozzolana started coming into being, and even today when you actually buy cement, there is a brand of cement which is called as Portland Pozzolana cement. And this pozzolana PPC, this pozzolana is basically anything which has a reactive silica content in it. So, the earliest example was the use of volcanic ash, and when you mix that with the lime, it started producing a chemistry which was not seen with plain lime kind of structures. Of course, beyond that, there is not too much of a development that took place until about the 19th century, and the 19th century is when cement came into being. Cement basically has its origins probably much before the 19th century. We have great scientists, one of them Vicat, and Vicat is something that you will come across later when you actually do your lab class with cement. but that's not until the 5th semester. So basically Weickert essentially looked at some combination of limestone which had a lot of impurities in the form of clay in it, and he saw that when you burn this limestone and clay together, the resultant lime that you get is excellent with respect to its binding characteristics. But later people realized it's not lime that you're getting, you're actually getting something else, you're getting cement. And the first person to realize this and understand the marketing potential was Joseph Aspdin. Although he was not the inventor per se of cement, but what he did was, instead of calling it a lime, he called it as a cement. Okay. He just called it as a cement, but he gave it a special name called Portland cement. So what he saw was, when this material that is obtained by mixing limestone and clay together, when it reacts with water, it results in the formation of a hard rock-like substance, and this rock was similar in appearance to a type of limestone that was found in Dorset in the United Kingdom. So from that, Joseph Aspdin gave it the name as Portland cement, and this Portland name got stuck with people, and people are still using it today, in spite of the patent having been obtained in 1824, and probably patent must have gone out 100 years ago maybe. The patent is no longer valid, but we still call the cement as Portland cement. Just like when you photocopy something, you say that I'm going to Xerox something. Xerox is not an English word, it's the name of the company that manufactured the earliest photocopiers. But even today, when you say you're going to the Xerox shop, but you go to, I'll challenge you to actually find a Xerox copy machine. You'll probably find some Japanese makes like Minolta or Sharp or Canon or something like that, right? So that's the power of branding. As far as cement is concerned, the brand is Portland, and even today in all bags of cement you see the name Portland. At least in India you see the name Portland everywhere being still used. So modern cement is obviously produced in sophisticated plants. If you go to a cement plant, you'll see the kind of control they have on each and every process of manufacture, with which they are able to get a product that has very low degree of variability, and that can be used to actually engineer the materials. On the other hand, if you go to a kiln where the lime is produced, many of you may have seen this while going by bus or train across rural areas, you see these lime kilns, people are not really controlling the process well enough. They just take the limestone, put it inside, burn it to some time, and then take it out. They don't have a control on the time, temperature, the pressure maintained inside the kiln, and so on. As a result of which, you don't get a product that is controlled with respect to its characteristics. So you may have something that is highly variable. On the other hand, cement, people have such control on the process that they can actually get a product that is very highly controlled with respect to its performance. Of course, today we don't just use cement, we also use mineral and chemical additives, and these enhance the properties of the concrete that we make with the cement. Okay? And this is something you'll learn a lot more with higher level courses in concrete. All right, so concrete itself as a material has been used for several years, I would say thousands of years, right? But people didn't know that it was called concrete earlier. Concrete is just an English word which means a mixture of different things. Concrete means a mixture of different things. So here obviously we're talking about mixing a binding material such as cement, we're mixing water, we are mixing sand, and we're mixing stone to make the composite material which is otherwise called concrete. And today we don't really have any other material which can have the level of adaptability, cost effectiveness, and durability as concrete, because of which concrete is still highly popular, primarily of course because of cost effectiveness. You can't really build structures with the same level of load carrying ability as you can build with concrete in a reasonable degree of cost. So people have built in plain concrete, right? There are several examples of plain concrete structures. For example, this wall here, which is retaining the soil, and you have this driveway on the right, which is again built with plain concrete. But there are obviously some limitations as far as building in plain concrete is concerned, because concrete as a material is excellent in compression, but very poor in tension. What do you mean by compression and tension? Compression is when you are applying the load onto the structure or onto the material. Tension is when you are pulling the structure apart. So concrete is not very good in tension, and because of this you need to strengthen it, right, in tension. And that strengthening in tension basically involves either using reinforcement like steel, which is a very good material when it comes to tensile strength, or using structures where you can optimize the shape. Like in the past, people built with domes and arches. In such cases, you allow the load path in such a way that only compression comes onto the material. there is no tension at all in such cases. For example, you may have seen pictures of these structures, the Pantheon Dome in Italy and the St. Peter's Basilica in Vatican City, which have some form of lime concrete used to create these massive slab structures on the top. These are basically dome shaped slabs and which have waffle like openings to reduce the overall weight, and you have even a circular opening in the end, in the center, to allow the light into the structure. Okay? So, these are concrete structures. They were built with concrete, but not the concrete that we know today. They did not use cement obviously, because cement did not come into being until the 19th century. This was built in the 2nd century, and of course, St. Peter's Basilica was in the 17th century. So, they did not obviously use cement, they must have used lime with or without some additives to make the concrete, which is basically mixing the lime with water, sand and stone, right. So, with a dome or an arch, you do not really get any tension, you only have compression, because of which the material is able to withstand quite easily. But when you go towards other forms, when you go towards more rectangular forms that we are used to seeing in construction, you need to start putting steel to reinforce the concrete. Okay. Now, you can see from this picture provided on the left, a typical scenario for reinforced concrete construction. You have the formwork, which is the wooden part on the outside, which provides a shape to the concrete structure, and then the reinforcement that is put inside the formwork, and then you put concrete into this entire segment to ensure that the concrete completely envelopes the steel, right. Because if you leave steel exposed to the atmosphere, what will happen? It will corrode. So, concrete has to cover the steel and entirely envelop it, but you only provide steel wherever the structure needs resistance against tensile loading. Where there is only compression, you do not have to worry about it, right. Where there is only compression, you do not have to worry about providing steel. You only provide steel where tension occurs in the reinforced concrete structure. So, reinforced concrete has given us a vast extent of possibilities which can define different types of shapes, different types of optimized uses and so on of the material combinations. Okay. This is a typical example of a reinforced concrete building. So, frame construction is something that started happening when people realized the potential of reinforced concrete. A frame construction simply means you build the vertical, that is the columns, and the horizontal members, that is the beams, right. You just build a frame out of the columns and the beams, and then you infill the walls later. Of course, beams also implies that you are having the floor slab built along with the beam. So, your frame is your column, beam and the slabs, which are the horizontal members, and later you fill in the space between the columns is the wall, and this wall can be filled up later. So, in this process, what is different from a conventional masonry construction? In a conventional masonry, the load is taken by the wall, right. Load is taken by the walls. In the case of a reinforced concrete frame construction, the load will be taken by the slab, beam and column. The walls will be non-functional with respect to load carrying ability, but they will be functional with respect to providing weatherproofing, obviously, because they are preventing the outer environment from completely entering inside. So, you have the wall primarily as a separator of the building from the environment, right. So, this gives you possibilities of using unconventional materials as far as the wall is concerned. And today, if you go out to see real construction projects, you will see that the wall is now being built with concretes like lightweight concrete or aerated concrete. Why is that interesting? Because if you put air inside concrete, if you make it highly porous, the flow of heat and sound through concrete is increased or reduced? It is reduced, right, because heat gets conducted much easily through a solid than through a porous material. So, you introduce voids and gaps inside your concrete, which makes the heat flow much reduced. And if you are doing interior air conditioning, obviously, it retains that coolness inside much better rather than losing out this coolness to the outside. So, you can use combinations of different types of materials which are providing these interesting functional characteristics inside the structure, because now you have completely eliminated the need to make walls very strong. But only problem is, again, people realized that this is cutting down on the productivity, because you make the frame, but the wall takes its own time in getting hardened and built up. So, because of that, people started moving to the next stage, that is building walls also with concrete, with solid concrete. And this increased the speed at which the construction could be done, because now you can have a formwork system around the entire structure. You just fill up your concrete As soon as some level of hardening of the concrete happens, you lift up this formwork and build the next level. And this way you can go from floor to floor much faster. And if you go to any of the high-rise residential buildings that are being constructed in the city, you'll see that this is a system that they adopt, where even the wall has the same concrete that goes into the column and the beam. So because now you don't need to worry about other materials, you just need to speed up your project by using the same material throughout the structure. Of course, there is a disadvantage here, that your walls are not going to be as efficient anymore as before, right? Earlier, with the frame construction, you had the choice of choosing different types of materials for the wall, which could reduce the heat loading of the structure. But here, you're building everything in concrete, so it's probably not a great idea. But then, it speeds up the construction extensively, and you can now produce or you finish buildings in a matter of a few months, where you earlier take more than a year or probably up to 2 years. The same level of building can be filled up or can be constructed in probably half the time. Moving on from this technology of using concrete walls, you can now create almost entire segments of concrete, like an entire room can be actually fabricated all at once. And this is done by something like a tunnel form. So you see here, as shown in this picture, you have this you have the tunnel form here. All you do is fill up the concrete into the walls and also into the slabs at the same time. So concrete goes into the walls and the top slab at the same time, and you simply build up one level over the other. So that's called a tunnel form construction. Once again, very popular means of building very fast, especially with respect to high-rise buildings, for apartment buildings and so on. Right. Now, when you slow down your process because you need to marry steel and concrete, what you can also do is try to look for methodologies by which you can strengthen the concrete itself and make it respond in a positive way against tensile loads too. And this has been accomplished by the use of pre-stressed concrete. Okay? You'll learn later about what pre-stressing is and how actually it increases load carrying capacity of concrete. But overall, this pre-stressed concrete belongs to a segment of concretes called as precast concrete. Now, what is precasting? That means without really assembling the concrete or shaping the concrete on the site, I already make the components of concrete in a factory, I bring them to the site and simply stitch them together, right? And that's called precast concrete. The obvious advantage I get from precast construction is that now I can control the quality a lot better. I'm factory making these components. On site, there are so many different people who can actually spoil the appearance, right? The workmen need not be well trained, because of which the final appearance of the structure could be spoiled. But I don't have that issue with a precast structure, where I build in components at the factory, come to the site and simply assemble them, stack them up, connect them properly and so on. So pre-stressed and precast concrete construction is actually responsible for a lot of our infrastructure construction today, including your Chennai Metro Rail, and the figure on the right basically is an example of a Chennai Metro Rail construction, where you have these piers and you have these precast segments that are taken up and put next to each other. All you do is simply put a steel through it and stretch the steel and press the concrete in compression. So what are you doing here? You are applying a pre-compression to the concrete. That's why it's called a pre-stressing, okay, pre-stressing operation. Now, when you use the same in slabs, you can get a structure like this, which is shown on your left, where you have the column and the slab directly on top. There is no beams in this case. So you are strengthening the slab by pre-stressing it. So you don't need actually the slab to transfer the load to the beam anymore. You can have the slab transfer the load directly onto the column. And what is the advantage like this? You get much higher floor area rooms, right? You get a lot more room in the floor, which can help you put your false ceiling and have a much better efficiency with respect to your air conditioning. So a lot of advantages when we move from one material to the other, but at the same time, when we use the same material in different kinds of applications with different kinds of methodologies, we can actually totally open up a wide range of possibilities. Now today, the limit of this possibility today is printing of the concrete itself. Now in manufacturing industry and in medical industry, a lot of the components are actually 3D printed. What do you mean by that? The deposition of the material is done layer by layer to build up the entire material, right? So these days, even stents, which they put to clear blocks inside your arteries, even those can be actually 3D printed to the most optimal shape desired and sent inside your arteries to remove the blocks. Similarly, people have started realizing that a lot of the machine tools, the common way of actually machining it is to go to the workshop, start using these cutting machines to shape it, and then use the filing machine to ensure that it gives the correct dimensions and so on and so forth. But now what you're doing is, instead of actually taking a large block and cutting, you're taking small layers and printing on top of the layers to build up the entire module. So this aspect was taken up in construction also. Primarily from in the beginning, the idea was, what do we do when we encounter terrains where you can't simply provide sufficient material for construction, where conventional construction will not do? Like if we establish a base on the moon, where do we take the materials to start constructing on the moon? So can we send an instrument out there with the required mix of concrete inside that, which can simply go and start printing on the surface of the moon without having the need to put workers and carry a lot of material out there? So that was the origin of this idea, and people have started experimenting with this to a large extent. So there are several different people who are actually doing 3D printing around the world. Some examples are given here, like the Contour Crafting Corporation. There's Total Custom in the US. So you can see what happens in this case is the concrete mix is fed inside the printer, and the nozzle simply prints a layer of concrete and then deposits one more layer and one more layer and so on. So what is the advantage here? The advantage here is, in the past when you had to make with concrete, you had to put formwork, right? I showed you that in one of the previous pictures, right? This formwork that you have on the side. Now it is estimated this formwork actually takes up nearly about 20 to 30% of the cost of your construction, and nearly 60% of the time that it takes to actually build the concrete structure. Why does it take so long? Because it has to be assembled, and after the concrete is hardened, it needs to be disassembled. Now that time can really eat up into the productivity of your entire project. So that's where people think that 3D printing can provide a means of actually much faster construction projects. And so there are several attempts around the world where people have looked at 3D printing. There are some commercial successes also. People have actually produced smaller scale buildings and hotels with this. And of course, there's one example of a Chinese company which does this 3D printing. So they prefabricate these 3D printed components in the factory. You can see how this arm of this printer is moving and depositing concrete layer by layer, and that's the finished structure on the right. Each and every wall is finished on the right and transported to site where it's basically simply connected together. Okay, the question is, okay, what's the advantage of doing this when you can as well do a precasting in the factory and then go and connect on the site? Again, the advantage is when you do the precast, you still have to use the formwork. Here you are totally avoiding the use of formwork. Of course, in IIT Madras also we have done significant work on 3D printing. If you have visited the ground floor of the BSB, you can actually see the India's first 3D printed concrete structure, which is basically a modular 3D print. We did modules of 30 centimeters and then connected them using mortar. It's almost like connecting blocks, but with the printer that we had to print, that is seen on the left here, we could not build modules which were more than 30 centimeters. So we had to build 30 centimeter modules and then connect them. Now we are actually producing another structure which is much larger than this and which can be printed almost up to a height of about 1.5 meters without the need for connecting modules. Okay? So there's a lot more possibilities in this realm, and definitely by the time you guys are done with your bachelor's degree, there will be a lot more construction around the world which has been accomplished by 3D printing of concrete. Of course, I'll just show you very quickly some iconic structures which show why these materials have been very popular. So wood obviously has been a popular construction material. It's got excellent tensile properties, and because of that, it's extremely efficient as a building material. If you go to the Western countries like the US or Canada, you'll see often that people walk into these large stores and buy their own wood and construct their own house themselves, because wood can be shaped and jointed quite easily if you've learned the basics of carpentry, and the joints are quite strong. Wood is excellent in tension, because of which you don't really need very sophisticated engineering to do wooden houses. So wood is still a very highly preferred material of construction in those countries. Only problem is, of course, moisture and fire resistance and biological growth are some of the issues which can bring down this life of the wooden structure. Then you have, of course, masonry, which is commonly seen in many of our bridges, right? You see some examples of excellent masonry bridges from Europe. Of course, with masonry, again, poor tensile strength could be a factor that affects the usage. And biological growth. You would have seen in many masonry structures there are even plants and trees growing through the structure, because again you have porous mortar which is filling up the space between the bricks. And the brick itself is basically soil, right? It's derived from soil. So if it absorbs moisture, obviously biological growth can take place within the brick also. Bridges in steel, most of our railway bridges are in steel, but a lot of iconic bridges around the world are in steel. One of the bridges which is iconic as far as India is concerned is the one in the bottom. What is this? The Howrah Bridge, right, in Calcutta. It's a very popular bridge. The bridge on the top left is the Golden Gate Bridge in San Francisco, again another popular iconic bridge, right. And you have the Sydney Harbour Bridge on the bottom right. It's again, you see that every time during New Year's when they put the firecrackers, right. Right, concrete bridges again, you see them all over the world. The top left picture is from a very popular movie that you've seen, Harry Potter, right. This is basically the Glenfinnan Viaduct in Scotland. And then you have the Multnomah Falls footbridge in Oregon, US. You can see the kind of difficulties they must have had in actually assembling this kind of a structure in that place. Then you have, of course, Confederation Bridge in Canada, and you have the Great Link Bridge in Denmark, Sweden, which is actually an extensively long bridge. It also converts into a tunnel in between. So the road basically goes on a bridge and gets into the tunnel and then comes out again in a bridge. The Millau Viaduct in France again is a very popular structure that people often put in their presentations. Again, this is more bridges from the US. Composite bridges, again composites basically ensure that we can get the best out of two different materials by utilizing their strengths. Okay. For example, if we combine concrete and steel, concrete is good in compression, steel is good in tension. So you provide reinforced concrete, which is an excellent composite material. But now we are not just stopping there, we are also using other materials like fiber, right, fiber reinforced materials. Fibers basically provide at a very small scale, they provide excellent tensile resistance, and because of which fiber reinforced structures have a much better potential of resisting dynamic loading like earthquakes for instance, and also can perform a lot better than non-fiber reinforced structures. For example, here this is a stormwater channel bridge in the US. You can see here a glass fiber reinforced polymer deck which is used to actually construct this bridge, okay. And these are basically shells of carbon fiber which are then filled with lightweight concrete to be used as girder. So the concrete strength there does not really matter as much because the carbon fiber provides an excellent strength in the direction of bending, and the concrete simply envelopes this fiber and ensures that a proper matrix is made. What is a naturally occurring composite structure that you are familiar with? Naturally occurring composite structure. Yeah? Wood. Wood is a naturally existing composite structure. Why do I say it's a composite structure? If you look in the structure of wood, you have the fibrils of cellulose which are embedded in a matrix of lignin. Okay? So the fibers, along this direction of the fibers, when you try to stretch wood, it has excellent tensile characteristics. Okay? So wood is a naturally existing composite structure. Of course, wood has been used in several iconic buildings in India also, like this Padmanabhapuram Palace in Kerala. And brick masonry, of course, is all over the place, especially with our heritage monuments that you see in Chennai. A lot of brick masonry is used, right. And stone masonry, the best example is of course Qutub Minar. With concrete, you have several examples around the world, like the Petronas Twin Towers. Another interesting example obviously is the Burj Khalifa. Burj Khalifa is not entirely concrete. The first 600 meters is in concrete, the remaining 200 plus meters is in steel. And the interesting facet about this is that the 600 meters of concrete costs less than the 200 meters of steel. The 200 meters of steel on the top has no purpose with respect to people, right. The 600 meters of concrete is where all the people are, because up to 100 and something stories you have until that level. Okay. And this also has a very interesting record with respect to concrete technology. This is the highest level to which concrete was pumped from the ground. So concrete was mixed at the ground and pumped all the way up to 600 meters and delivered for the construction of the highest level of concrete in this building. But what happens when you start constructing these tall buildings? What is a governing factor? Is it the stability anymore, or is it the strength or the stability? Stability against wind, yeah, lateral loads. When you start constructing tall, you need to start thinking about designing against lateral loads, not just wind, even earthquake for instance, you need to have essentially components of design built in which can take care of these loads. Another interesting aspect about Burj Khalifa, of course, it came much after the downing of the Twin Towers in New York by Osama bin Laden, right? What happened there? Those structures were made with what material? Steel. Those were steel framed structures, right? Just like the one on the right, that is Sears Tower in Chicago, another iconic building. So World Trade Center in the US, in New York, the Twin Towers were actually steel frame structures. So when one floor gave way, the rest of them simply collapsed. Progressive collapse is something that they did not have, they did not actually design for in the World Trade Center buildings. But as far as Burj Khalifa is concerned, even that has been taken into account, okay. So if a progressive collapse happens, for example, at this level here, the structure may collapse, but it will stop collapsing at this point here. You can see this massive raft that has been provided. So that basically cuts off one segment of the building from the other and prevents the entire building to collapse right on top of one another, just like the World Trade Center did. So we adapt, we learn from our past problems. Of course, nobody could have thought about an airline crashing into a building. That's something totally unthinkable. Nobody does a design for that. But nevertheless, we adapt and we learn from our past to try and build something different. Okay. So today, of course, a lot of glass is also being used in structures. So glass and steel are popular choices with respect to your high profile structures. Even Guggenheim Museum in Bilbao in Spain, it's a titanium clad steel and limestone which is combined together to give this very interesting sort of an appearance. And of course, dams in concrete, you see several hundreds of them all across the world. So where are we going from here? We have looked at how materials and construction practices evolved, how different materials led to various types of performance and functional characteristics, and how we were limited by the characteristics of one material to ensure that we could overcome that by choice of combinations of that material with one other one and so on. So what are the challenges that we have for the future? One primary challenge is that our resources are going down. We have dwindling resources, especially if you think about cement, which is the most commonly used binding material in the world. Manufacture of cement utilizes vast quantities of limestone from around the world. And it is estimated that if we continue to produce cement at the same rate, we'll run out of those limestone reserves probably in 50 to 100 years. That means there won't be any cement beyond that. And so people have started looking at alternatives to using cement and concrete. So alternative materials again is something that we need to wake up to the possibility of and start thinking about utilizing as much as possible. In most cases, what happens is the construction materials are highly heterogeneous, because I'm primarily talking here about concrete, which is the most commonly used construction material. This heterogeneity leads to an accompanying unpredictability. We can't really model these materials well enough, and because of that, we can't predict how long they'll withstand a particular set of loading and environmental conditions. Steel, on the other hand, we are much more capable of understanding because it behaves in a very specific fashion. Steel components are factory produced. When they come to the site, all you need to do is connect them, right? The characteristics of the steel are governed by how it is produced in the factory. Concrete, on the other hand, a lot of it is applied or directly made on the site, and because of which a lot of variability is introduced into the formulation of concrete. Increasing lifespan of materials and service life of structures generally says that there should be some aspects that we need to look at from the point of view of modeling these materials. Again, I said that heterogeneity leads to difficulties in modeling, but then we need to model because we can't keep on testing to ensure that the material is safe. We can think about how to generate well accepted models which can be applied to the study of structures over the long term. And again, choosing sustainable options is something that is becoming very important today because we are using a lot of resources, we are using a lot of energy. We need to choose technologies that can minimize on these. Okay? So tomorrow when you become engineers, you'll start hearing of these terms more often. Carbon credits is one term that you'll hear of quite often. Green rating, embodied energy, life cycle assessment. It's no longer going to be strength, durability, workability. No, you'll start thinking about how to make the technology in such a way that your carbon credits are obtained. You can reduce the embodied energy in the structure, get a green rating for your building, and have numbers with respect to life cycle assessment. So these cannot be just buzzwords. You need to get the true meaning of these to really implement these in construction. So with that, I'd like to just end by saying that we are obviously at a very exciting stage with respect to the kind of applications we have with conventional materials and with new materials coming in, which can strengthen our understanding of existing construction technologies. People used to say, mock civil engineering and say it's a brick and mortar profession, but the vast variety of materials and the construction process that we use clearly shows that civil engineering is no longer a brick and mortar profession. So thank you all for your